Well, hello everybody, and welcome to another lesson in pre-calculus. And actually, we're getting close to the end of all our topics, and this is that kind of the second last major topic is complex numbers, or more precisely, the trigonometric form and exponential form of complex numbers. I'm assuming that you've seen complex numbers before, maybe in Math 128 or some other course. But let me remind you what a complex number is. It's a number of the form a plus bi, where a and b are real numbers, and I is the imaginary square root of -1. Okay, so I is not a real number. It doesn't appear on the real number line. We told you in the past that you can't take the square root of a negative number, and then we do. Okay, we sort of created one or discovered one, but the thing you want to realize, this is independent of the real number line. Okay, so and I is has the property basically that if you square I, you get -1. There's also a negative square root of -1, that's minus I, and so these are all examples of complex numbers. Okay, 2 plus 5i, 3 minus I, 7/3 minus square root 2 times I, right? This 7/3 and square root 2, those are real numbers. 6i, and even 7, okay? Because 7 can be written as, 7 plus 0i. So every real number is a complex number. So just so you know that. And then adding and subtracting complex numbers is pretty easy. Because all you are doing is adding and subtracting the real parts and the imaginary parts. Multiplying is a little bit different, but it's not that much different than multiplying, two polynomials and just realizing that I squared is -1. So you don't really have to memorize this. Okay, you can just go ahead and FOIL this out, and we'll do an example in a minute. We can also divide complex numbers as long as the number you're dividing by is not 0. So we do that by conjugating, rationalizing the denominator by multiplying and dividing by the conjugate of the denominator, and then we get this. We get some fraction plus another fraction times I. So that is a complex number. And remember, the conjugate is what number we get when we replace the imaginary part with the opposite of the imaginary part. So the conjugate of a plus bi is defined to be a minus bi. So just to give just a real quick example how this works. So if alpha is 3 plus 2i and beta is -7 plus 4i, alpha plus beta, that would be 3 minus 7, -4, 2i plus 4i, that's 6i. And alpha minus beta, that would be 3 minus -7, that's 10. 2i minus 4i is minus 2i. And alpha times beta, it's 3 plus 2i times -7 plus 4i. FOIL this out, this is -21 minus 14i plus 12i plus 8i squared. Okay, and of course I squared is -1. Okay, so this is -21 minus 8, so this would be -29. And then this would be -14i plus 12i, so that would be minus 2i. Okay. And then you can divide this if you want. So we do the multiply and divide by the conjugate of the denominator. And when you do this, the denominator is always going to be a positive number. It's going to be 49 plus 16. So that is 50. 49 and 16 is 65, I think. Okay. And then this will just be minus 21, minus 14i, minus 12i, and minus 8i squared. And so this will be 21, minus 21 plus 8, because the I squared becomes negative 1, so this is negative 8 times negative 1, so that's positive 8. 8 minus 21 is negative 13. And this is negative 26i. Okay, and so this will be negative 1365 minus 26 over 65i. Okay. Okay, I don't know, maybe you could simplify these fractions, but I don't want to do that. Okay, so that's how you can do all these wonderful operations. All right, now the point of this is just review. The point of this lesson is to show consider a different form for complex number. This is actually called the rectangular form. Of a complex number. What we want to do is look at the trigonometric form and the exponential form of complex number. Okay, and the trigonometric form comes from the result that the complex plane looks very much like the usual xy coordinate plane that we've done most of our work. Okay, one difference is that instead of this in the coordinate plane, we have this horizontal axis is the x-axis, and the vertical one is the y-axis. And the points are actually, have coordinates. In the complex plane, the points are actually complex numbers. So the point A, B is now replaced with the complex number A plus BI. And this is the horizontal, the x-axis now is the real axis, and the vertical axis is the imaginary axis. Okay. But geometrically, we can see that this distance and this distance will be the same, and this angle will be the same. So the complex number still has a certain distance from the origin, and this ray makes a certain angle with the horizontal axis, this theta. And that theta and that r is enough to uniquely determine where the point is. So we call so if z is a complex number, the modulus of z is defined to be just the distance from the origin, which can always be computed as the square root of a squared plus b squared. And the angle that this makes with the real axis, positive real axis, is called the argument of z, and we call that theta. And because so r and theta basically are just the polar coordinates of the corresponding point in the coordinate plane, and we are want to be unique. So we here r is always going to be greater than or equal to 0, and theta is always going to be between 0 and 2 pi. And then by using the coordinates, change of coordinates, we get a is going to be r cosine theta, b is r sine theta, because a is like the x coordinate and b is like the y coordinate. And the tangent, I should say somewhere, I should keep in mind that the tangent of theta will be b divided by a. Okay. All right, and then from there we can find theta by taking the inverse tangent and then subtracting it from pi if we have to, if a is negative. So with all this in mind, z now can be written as, if we factor out the r, this is r times the quantity cosine theta plus I sine theta, and this is what we call the trigonometric form of a complex number. And shorthand, we sometimes write r cis theta, where cis means cosine, imaginary, square root, and sine. So if we just do some examples here, 1 plus I, and when you're first doing it, it helps to write, maybe draw a picture here. Okay, this distance is going to be, so in this case, a is 1, b is 1, so r is going to be the square root of 1 squared plus 1 squared, so it's the square root of 2. And we can clearly see, hopefully, that this angle is 45 degrees, but really it's pi over 4. We always use radians when we're doing this. Okay, so theta is pi over 4. And so we could, so z is now going to be the square root of 2 times the cosine of pi over 4 plus I times the sine of pi over 4. So that's a trigonometric form. For what about negative I? Negative I is on the imaginary axis, but it's down here. Okay, so this distance we can clearly see is 1, hopefully. And this angle is going to be 3 pi over 2. Okay, so r is going to be 1, and theta will be 3 pi over 2. Okay. So you can then you can write it this way. So then I won't write it, but it would be 1 times the cosine of 3 pi over 2 plus I sine of 3 pi over 2. What about square root of 3 minus I? In this case, A is the square root of 3, B is negative 1. So R is going to be square root of 3 squared plus negative 1 squared, all under a square root. So this is going to be the square root of 3 plus 1, which is the square root of 4, which is 2. And then theta, the tangent of theta, is going to be negative 1 over square root of 3. And this is one of the tangent values I'm asking you to memorize, right? And this is going to be, well, normally we would say negative pi over 6. If we were to draw this, the corresponding point would be over here, okay? And we'd say, okay, this angle is 30 degrees, so it's in the opposite direction, so it would be minus 30 or minus pi over 6. But because theta has to be between 0 and 2 pi, we can add 2 pi to this, so theta will be 11 pi over 6. Okay, if we want theta to be positive in this range. Okay, okay. You could have also just taken use your calculator, in the inverse tangent of this number, and that would give you, that would give you negative pi over 6, and you still have to add 2 pi to this. Okay, 2 plus 5i, that's going to be up here. So here's 2, here's 5, so this is 2 plus 5i. Okay, now so the tangent, so r is going to be the square root of 2 squared plus 5 squared, which is the square root of 29. We'll just leave it like that. And then theta is theta is going to be the inverse tangent of 5 halves. Okay, this is going to be we just take the inverse tangent because obviously you can see that this angle is in the first quadrant, so the inverse tangent is that. So that's what this is. So for this is going to be r equals the square root of 29, and theta is the inverse tangent of 5 halves. And let me see. I think you would, if you really wanted to see what the value is, this is approximately 1.19. 190. Okay. What about this last one? Negative 2 plus 5i. And I go over here. Okay. So that's over here. It's in the second quadrant. Okay. So our angle is going to look like this. R will still be the square root of 29, because negative 2 squared plus 5 squared is 29. Well, we can see that this angle, this angle plus this angle here was going to be the same thing as what we had over here. It's this from here to here. It's the inverse tangent of this angle is the inverse tangent of 5 halves. Okay. So theta is going to be, well, this angle plus this angle is pi. So theta has to be pi. So if this is theta, theta is going to be pi minus the inverse tangent of 5/2 in this case. You could also just say theta could be, you could also say that this would be the inverse tangent of negative 5/2. But that would give you an angle in this quadrant, okay? And then you would have to add pi to that. So either one works, and theta turns out to be approximately 1.951. Okay. All right. So that's theta, and this is r. Okay. So really, in a way, we haven't done anything new. We're just finding polar coordinates. The only difference is the point on the plane is really a complex number. Okay. So get some practice with this, and we'll see what happens in the next part.